the cross product. Let vector A equal a1, a2, a3, and vector B equal b1, b2, b3. Then the cross product, A cross B, is the determinant of the matrix ijk, a1, a2, a3, b1, b2, b3. In case you haven't done determinants before, I'll show you how to do the determinant of this one. So what we do is we take really any element, but I'm going to take the first row one at a time, meaning I'm going to take the unit vector I, and then we want to cross out the row and column that has the I, like that. And then we're going to do the determinant of the 2 by 2 matrix left over. So we're going to do I times, and the determinant of the matrix that was left over would be A2 times B3 minus A3 times B2. Then we're going to go to the next element in that same row, and it's going to be J, but it needs to be minus, so minus J. And then we would look at the row and column with J and do the determinant of the 2 by 2 matrix that's left over. So we have J times A1 times B3 minus A3 times B1. And then finally, we need to do the last element of the row, which is going to be K, and this time it's going to be plus K. So if we had more rows, it would be plus minus, plus minus, plus minus, but cross products are done on 3 by 3s. And then we would cross off the row and the column that had the K and do the determinant of the matrix that was left over. So we do K times, and then A1 B2 minus A2 B1. And that's how we find the cross product of two 3 by 3 vectors. Let's talk about some properties of cross products. Some of the more common ones that you might see. So the first property we're going to talk about is what happens if we do the cross product of a vector with itself. Well, the cross product of a vector with itself is always the zero vector. That is, it would be 0i plus or minus 0j, doesn't really matter, plus 0k. So the cross product of a vector with itself is always the zero vector. Property number 2. A cross B is always perpendicular, and I'll use that symbol for perpendicular, to both vector A and vector B. Some other properties that may be important when you're going forward. A cross B does not equal B cross A, but instead equals the negative of B cross A. So when you switch the order, you get the negative of the resultant vector. And so that's one important thing I should mention here, kind of alluded to. Whereas the dot product of two vectors is a scalar, the cross product of two vectors is a vector itself. And another one, so the distributive property, so A plus B cross C equals A cross C plus B cross C. And remember that the order does matter. So let's do an example of a cross product between two vectors. Let's choose the vector A equals, just say 1, 2, 1. We don't need to make it complicated. And B equals the vector, say 2, negative 1, 3. Then A cross B would be the following. We'll set up our matrix, get the determinant. So I, J, K, 1, 2, 1, and then 2, negative 1, 3. And then we do I times 2 times 3 minus 1 times negative 1. So in case you weren't seeing, so 2 times 3 minus 1 times negative 1. Then minus j. And then we do 1 times 3 minus 2 times 1. So 1 times 3 minus 2 times 1. And then plus k. And we'll do 1 times negative 1 minus 2 times 2. So negative 1 minus 4. Putting that together, simplifying, we get 7i, and then minus 1j minus 5k. And that is the cross product of A and B. Now, I'm not going to prove property number 2, but let's take a look at it, see that it certainly works in this case. Where property 2 says A cross B is perpendicular to, I said to B, let me fix that real quickly, to both A and B. So how would I show that A cross B, and let me rename that, I'll call it vector V just to make it a little simpler. How would I show that vector V is perpendicular to A? Well, I would do the dot product. So let's do the dot product of A with V. And recall, if the dot product of two vectors is 0, then the two vectors are perpendicular. So if I do A dot V, I would do 1, 2, 1, dot 7, negative 1, negative 5. And we get 1 times 7 plus 2 times negative 1 plus 1 times negative 5, and that indeed does equal 0, which means A is perpendicular to V. Similarly, B dot V would be 2, negative 1, 3, dot V, 7, negative 1, negative 5, which equals 2 times 7 plus negative 1 times negative 1 plus 3 times negative 5. Once again, the dot product is 0, which means that A and B are both perpendicular to the cross product of A and B. Now, I recommend going back and proving some of these properties on your own. There are other properties as well that you might run into. Let me prove that first property that we talked about, where A cross A equals a 0 vector. And let's set up A cross A, making our matrix. So we get I, J, K, A1, A2, A3, A1, A2, A3. And then doing the cross product. So it's I times A2, A3 minus A2, A3. I think you get the idea already. Minus J times A1, A3 minus A1, A3. And then finally plus K times A1, A2 minus A1, A2. And notice that we get 0i minus or plus 0j, doesn't matter, plus 0k. Let me talk about one theorem. I'm not going to prove the theorem here, just because the algebra gets pretty messy, but we will use the result of the theorem in just a bit. So let theta be the angle between two vectors A and B. Then the magnitude of A cross B equals magnitude of A times the magnitude of B times the sine of the angle between them. So once again, the proof is pretty messy and pretty involved algebraically. But let's use this theorem to get a geometric interpretation of the cross product. And I'm going to draw a picture. So let's have two vectors, A and B. I'll put A down here, and I'll put B as the one that's slanting up to the right. And then I'll drop a height here. I'll call that H, and I'll put the angle theta between A and B. And let's finish off the parallelogram. Pretend there was the rest of a parallelogram, something like this. Notice that the area of the parallelogram is base times height. So B for base, not B for the vector B, and then base times height. Now, the area of the base, the length of the base is the magnitude of A. And the length of the height is the magnitude of B times the sine of theta. So using the theorem above, we see that the area of a parallelogram with sides, I'll add that here, with sides A and B is equal to the magnitude of A cross B. In the next video, I'm going to do a couple applications of the cross product. So if you'd like to see some more problems that you've probably seen in a textbook, just go ahead to the next video.